NumPy is basically a Python library that lets you do numerical computation. It's a little bit like MATLAB. If you ever worked with MATLAB, then you're going to see a lot of similarities here. And the reason why NumPy is so popular, actually, I think NumPy is probably the #1 most used library in Python. I'm not sure, don't quote me on that, but I believe it is. At least for me, the only reason why I use Python really is because of NumPy, because it's great. Not the only one, but the main one is because of NumPy and because it's great. And the reason why NumPy is so great is not only that it makes it very easy to do a lot of computations in matrices and vectors, but it also very fast. And because Python in general is very slow, okay, in general. But NumPy is actually not written entirely in Python. It's written in C, or in otherwise in very low level code. It's compiled into libraries and into executables and binaries. And then you call it from Python, but actually most of the operations that are executed by NumPy in hidden from you are actually being done in a binary executable that is native to your system, and that uses all kinds of optimizations, linear algebra optimizations, and all kinds of vectorizations and everything basically that your computer can do in the fastest way possible. NumPy allows you to do that from Python, because it's not written actually, most of it in Python. It has Python bindings, as we say. You call it from Python, but it is actually executing as native code. So it's very fast and it's very flexible, and basically it's almost like a standard in every data science pipeline or workflow in Python. Basically NumPy is usually used as a standard for data and for matrix operations, math, and everything. And the way you use NumPy is by importing it. I didn't talk about importing in the previous notebook. But this is how you import an external library into Python. I'm saying import NumPy here. So that would be enough if I wanted. I could just do it like this. And then I can just use the name NumPy everywhere I want to call things and to do whatever I want. However, it is more common to actually write it like this: import NumPy as NP. And basically all it does is just rename NumPy to NP, so that you can, since you're going to be calling it millions of times, then you might want to just make it a little bit shorter to make it easier, right? So then you can do it like this: import NumPy as NP. And then afterwards, you can simply use this NP module and call everything that has to be called in order to do the maths and everything. So the very first basic thing you must know about NumPy is that everything is based on NumPy arrays. So arrays are not lists, okay? But even though sometimes you may confuse them, but arrays are different than Python lists, okay? An array is like a low-level data structure that is managed by NumPy. And it's much faster than Python lists, but it's also a little bit more restricted in a few ways. So for example, this is the way you create an array, by calling the function np.array. So np, as you remember, is the NumPy module. And then you call np.array, which is a function within the module. And that makes an array for you, that creates an array for you. How you want to create that array depends on what you want to be in the array. So for example, in this case, I'm saying, look, I want an array that has these elements, 1, 2, and 3, okay? And basically it takes your list 1, 2, 3 that you put here, and it turns it into an array, which is more like a low-level thing. So for example, if I print the type here of A, you can see that the type is numpy.nd array. So don't worry too much about this nd. This basically means like n-dimensional, but you don't have to worry about that too much right now. Just think of them as arrays. And arrays have shapes, which is quite interesting, and it starts to become a little bit more complicated. The shape of an array is how many axes it has, or how many dimensions it has. If you don't understand what that means, I'm gonna show you, and you're gonna understand in a minute. So for example, the shape of this array that we just created here is a tuple with just the number 3. So basically it says, okay, there's only one axis in this array, And this axis has 3 elements because it's just a simple one-dimensional array here, 1, 2, 3. Okay, so the shape of this array is one axis with 3 elements. And then if I print A, you can see that it's just 1, 2, 3, basically the same as a list, but you may have noticed that there are no commas here. If you printed this list here, you would see comma 1, comma 2, comma 3. In this case, there are no commas, just 1 space, 2 space, 3, and that makes it clear that it's an array and not a list. Okay, and as you can see here, arrays are a little bit like this in the sense that you can change them. So for example, A0 equals 5, and then you can see now it's 5, 2, 3 because I changed the first elements to be 5. And most, if not all of those slicing techniques that you've seen in the list can also be done with arrays, but with a little bit more stuff that can also be done, as you will see. Now, up to this point, you may be thinking, well, an array is just like a list. It doesn't matter really too much. It's just, I guess it's just a wrapper on top of a list. Well, yes, if you do it like this, but no, if you do it like this. This is a rank 2 array, as we say, because this has, let's say, in a way, like 2 axes or 2 dimensions, as you can see here. Yeah, this is how it looks after you've created the array and after it's in memory. And now you can see that basically this array, why do I say that it has 2 axes, so to speak, or 2 dimensions? Well, dimensions are, it's a little bit confusing. I will refer to them as axes from now on, so we don't confuse it with actual like data dimensions. So I'm gonna say axis, right? This has 2 axes. Why? Because it's basically a 2-dimension, yeah, it's hard to not say that. Basically, it's an array that has rows and has columns. So basically there's 2 axes. I can go what is the first row, what's the second row, and then I can also see it as a one column, 2 columns, 3 columns. Okay, so this has 2 rows. The first row is 1, 2, 3, and the second row is 4, 5, 6. Just a second, I will answer that after I finish this cell here. So this is the array. It has 2 rows and 3 columns, and basically these are the axes. One axis is the row, and another axis is the columns. Arrays can have any number of axes as you want. Like for example, you could do a 3-dimensional array with 3 axes, and then that would be like a cube. It would have an x, a y, and a z axis, and you could have values all over all of them. That would be like a full cube full of values. In this case, it's like a Cartesian plane where you have the x-axis and the y-axis, and then you have values for each, let's say, step in them. And as you can see here, the shape is 2, 3. So that means I have 2 rows and 3 columns. Okay, and you can see that since the tuple here has 2 elements, then that means you have 2 axes. The first axis has 2 elements because we have 2 rows, and the second axis has 3 elements because we have 3 columns in each row. Okay, and it's very structured. Okay, this is not like a list where you could have like a row with 3 elements and another row with 2 elements. That wouldn't work. If the second axis, or like the columns, has 3, then it has to be 3. Like it has to have 3 columns in all rows. So it's really a matrix. Okay, it's not just something where you can put whatever you want in it. And then there is this special type of indexing here where you can do it like this. So for example, B 0, 0, I'm basically saying I want I will answer all the questions after this cell, guys. You can keep sending them. I want to have the first element from the first row, I want to have the element from the first row and the first column. So row 0, column 0, and then you see number 1 here, because this is the row, this is the 0, 0 number here. And then I can say, for example, B1, 2, and that means I want the element that is in the second row and the third column. So then you will see the number 6 here because it's the second row, third column. Okay. And also you can index the row directly. So if I say just B0, then I mean I want this, the first row, and then you can see the first row here. Okay, so this is very flexible and very interesting way to index your array. How to create, so two questions we got. One is there a built-in function for matrix? You don't have built-in function for matrices, but you have a lot of functions that are not built-in, but they come from the NumPy module. And that's what we're gonna see very, very soon here. And then David asked, how do you create a 3 or 4 rank array? Well, I could, you could create it in many different ways, which is actually what we're gonna see in the next few cells. Creating it by script from hand like this would be a little bit complicated because you would have to add a lot of brackets, you know, like this, and that would become kind of strange. But I will show you in these cells here how to do it. Are arrays mutable? Yes, you can simply assign values like this, and you will see other more advanced ways to do this. But yeah, arrays are mutable. They're basically like, they're in memory, and you can do whatever you want with them, change the elements, change from slices, just like we did with lists. But yeah, they are mutable. So these are other ways of creating arrays. So for example, David's question, how do you create a 3 or 4 rank array? If I did it like this, now I have an array that is, let's call it this thing Z, and then I can see the shape of Z. And as you can see, well, of course, because I asked for explicitly for an array with a shape of 2 by 2 by 2. So this would be like a cube with 2 elements in the 2 rows, 2 columns, and then two whatever you call it when it comes into the 3rd dimension, right? So it's basically 2 by 2 by 2, and then that would be in total, you would have here 8 elements in it. So basically this is a way to create an array by simply filling it with zeros. I will answer that question, just keep them coming, I will. But basically, yeah, you see here we have 8 elements in 3 axes, and they're all zeros because I called np.zeros. So regarding the question from Bodies, is there a built-in function for matrix? This is not a built-in function for a matrix, but it's a function that comes from the NumPy module. So it's kind of like a built-in in a way, but instead of calling it from the Python language itself, you call it from the actual module that you imported, right? And it creates a matrix for you full of zeros. You can also create a matrix full of ones. So for example, I could do something like this. This would be, as you can see, much larger because this is a rank 5 array where you have 1 element in the first axis, 2 in the second axis, 4, then 7, then 8, and so on and so forth. It's hard to visualize this. It's almost impossible to visualize. But basically, as you can see, since the last one is 8, you can see there are 8 elements here in each of these like sub-arrays. But it's almost impossible to visualize this. So you can do actually something like this instead, or that's, I guess, a little bit easier to visualize. You could also create it by just giving 1 value and then making it a full array with that value. So in this case, you can see, for example, it's a 2 by 2 array with 7s, full of 7s. You have this I function that gives you the identity matrix, as you can see here. Like this is a, well, in this case, it's a 3 by 3 identity matrix, which is, in this case, actually with 2 axes, right? So it's not 3 axes, it's just 3 by 3s because the matrix, let me print the shape here. So, yeah. Yeah, you can see the 3 by 3 matrix because it's a little bit different. It's not a rank 3. It's the matrix is 3 by 3. And you can also generate arrays by simply taking lots of random values like this. In this case, I'm asking for an array full of random values that has 3 rows and 4 columns here, and then I get this weird thing here. Let's see the questions. I'm curious about the call by reference and by value in functions or arrays. What is your take on this matter? Maddie, if possible, I think I will take this offline with you because unfortunately I have too much to talk about right now and I don't have the time for that, unfortunately. So yeah, So then we have array indexing here. Array indexing follows a lot like list indexes, but you can or you must, well, not must, only if you want, but you can do the slicing per axis. So for example, in this case, yeah, in this case, sorry, bodies, you said pointer. I don't know what you mean, unfortunately. If you want to tell me. But anyway, if you see here, we can slice the axis individually. Like, so for example, in this case, I have this array that has 1, 2, 3 rows and four columns. And then I'm slicing each axis separately. So it says, for example, I want the first and the second rows, so the first 2 rows, plus the columns from 1 to 3, not including 3, right? So then I get 2, 3, 6, 7, because this is basically first and second rows, and let's say the second and the third column, and then I get 2, 3, 6, 7, which is the result here. Okay, so you can basically, the takeaway message here is you can slice each axis individually, and that will give you this kind of complex but very useful slicing like this. Okay. One important thing to know about when you slice a vector is that a slice of an array is a view into the same data. Okay, so it's not a new array. When you get this thing, this is not a new array that has 2 rows and 2 columns. This is a view into the original array. So for example, if you here, like if I take a certain slice or a certain element and I assign a value to it, so where is, oh yeah, okay, it's right, sorry, B is a slice, yeah. So you can see here that the B is the slice of A, and I just took an element of B and I assigned a value to it. But then when you print, I'm just going to print A as a whole, I think it's better. Yeah. So you see here, for example, yeah, so you see here I have, well, now it's changed. So you see I have B as a slice, then I take B and I assign a value to it. And then when I print A, you can see this 77 here, right? Because this thing this B thing is a view into the array A, okay? It's not a new array that has been created after slicing. So be careful with this. When you slice, and if you change a slice, you're changing the actual original array, okay? Question from Maddie. The modules are extensions of Python 3 that enable and provide us with what a data scientist needs to treat data. These modules that I'm talking about, yes. NumPy, Matplotlib, that I will hopefully talk about it soon. Oh, it is quite powerful. Yeah, you can bet it is quite powerful. That's why it's probably the most popular language nowadays. Well, it is the most popular language for data scientists. Yeah, this is interesting. Well, you can mix integer indexing with slice indexing. So for example, here I'm slicing with I'm slicing and then using an integer here. So it's basically the same. As long as you do one different thing per axis here, then you get what you want here. You don't have to like slice both of the axes using a colon here or anything. You can mix up. It doesn't matter. Yeah. I will have to skip some stuff, unfortunately, which I don't believe it's super important. You can take a look later. I will get back to this. Whatever I skip, I will get back to it in the next lecture because we're going to have another Python question. Oh, sorry. We're going to have another Python lecture in, I think, a couple of weeks. So like Bodies has endless questions. And you can bring them to the next lecture maybe, or you can put them on the Moodle or Slack, and then I will try to answer as much as I can. But for sure, you have to do your own research anyway, because I mean, it's huge, right? It's a lot of stuff. But anyway, whatever I'm skipping here, I will bring it back in the next lecture because I don't think it's super fundamental right now. Basically, remember that different than lists, Python arrays have data types, okay? So they actually have data types. They're not like lists where you can just put whatever you want into an array. an array in itself has a data type. Because this is like, we're talking about low level math here. So it needs to have types in order to make it correctly. But you can also force particular data types. Like for example, in this case, I created an array with ints, and you can see that the type of this array here is the D type, as you say, the data type is int64. So it's a 64-bit integer. And then this one I created using floats. So it's a 64-bit floating point. But you can also, in this case doesn't, let me do it like this. Yeah. So in this case, for example, I created Z, but I forced this to be an actual 32-bit integer array instead of a 64-bit because I need to save on memory, for example. And then you can see I forced it, and now it's a different one. So the question from Agnesa. So the main thing that differs the array from the list is the multi-dimension property. From an outsider point of view, maybe yes, but technically speaking, it's also implemented differently. So when you actually start doing math with it, which is what we're going to do right now, then you're going to see that there's a lot of stuff that you can do with arrays that you cannot do with lists because of the internal implementation of it. Okay, so it's much more low level and much faster than lists. Array math, this is probably the most important part. Suppose I create two arrays here. One is X and the other is Y. I've created them here with integers, but I force them to be floating points, for example. And then look what happens here when I do X plus Y. So before, when we were looking in Python, X plus Y only worked when X and Y were actually numbers, right? So like 1 plus 2 or 4 plus 5 or whatever like that. In this case, X and Y are both vectors. They are not vectors, sorry, arrays, NumPy arrays. And look how interesting it is. When you do X plus Y, basically you sum element-wise all the elements from X and Y. So it becomes, 6, 8, 10, 12, because it's, you know what, let me format this to make it a little bit easier to see. So you can see, for example, this is 6 is 1 plus 5, 8 is 2 plus 6, 10 is 7 plus 3, and 12 is 8 plus 4. So basically what NumPy does here is it does an element-wise sum of all elements here. Evan asked, but could you create multidimensional list? Yes, you could by making a list of lists, but you could not do multidimensional slicing on it. You could not slice the columns and the rows at the same time like you can do with arrays. And you cannot do, for example, what we just did here, X plus Y, and then get an element-wise sum. You would have to implement it yourself, I guess. Yeah, it's very useful for regression for sure, for any machine learning actually. So this element-wise operations, they're everywhere, okay? So X plus Y, and then for example, X minus Y, of course, is the same thing. You have X times Y, again, same thing. And you could call, for example, np.square root of X. And again, you can see here that actually what we get is the element-wise square root of X. So X was this thing here, 1, 2, 3, 4. And what we get here is the square root of 1, the square root of 2, the square root of 3, and the square root of 4, all at the same time. Okay. And as you can see, I just also added some examples here that you could do the same thing by actually calling a function from NumPy. So you could say like np.subtract X and Y, exactly the same result as you get by just typing X minus Y. I just want to make sure that you guys understand this, because this is probably like 99% of what you will be doing in the next 2 months or so. So when you do something like this, or let me focus on this. When you do something like this, you're summing every element of X to every element of Y, okay? And this is done very, very fast. So I'm not saying that you're looping over the points of X and Y here. This is not what's happening. I mean, maybe this is what's happening, but it's happening in a native code, in binary code. So if you have like X and Y, and both of them have 1 million elements, if you try to do this in Python, it's going to take minutes, I guess. But if you do it in NumPy, it's immediate, okay? It's almost instantaneous because it's really, really, really fast. And it's, if possible, if your processor can do like parallel vectorized operations, it will do that automatically for you. So I really want to stress this. This is very, very much like a performance thing. So you must, when you want to do something like this, if you want to add like to list or to arrays, or if you want to do any operation in the two arrays that is going to be done element wise, you should do it using NumPy and NumPy syntax, not using Python syntax. Because if you do it in Python, like looping over the arrays or something like this, it's going to be very, very slow. But if you do it using something like this, like NumPy syntax, this is going to be very fast. So you should always try to do something, whenever you can, do something like this vectorized. Let's go on and you will see what I mean. Now, very important thing to notice, x times y here is element-wise product. This is not matrix multiplication. If you want to do matrix multiplication, then you actually has to call this function called dot, which is a dot product, let's say, right? But it's because the matrix multiplication is basically a dot product, it's the same thing. So if we want to, for example, multiply x times y, in this case, I don't have it here, but I can put it here. You can see where we're going to get there. Yeah. So if I want to multiply x, do an actual matrix multiplication of x with an I actually do x dot y. I don't do x times y. Okay, you can see the difference here. Like this is 5, 12, 21, 32, and this is 19, blah, blah, blah. So this is the actual matrix multiplication as you remember from math, you know, all those complicated row times of column and so on. This is the dot product, not the asterisk here. So keep that in mind, please. And as you can see, you can also do dot products between matrices and vectors, for example, or vectors and vectors, doesn't matter. So you can still do it. For example, v dot w, in this case, we're doing a dot product of two vectors, and the result of that is just a number. So you see 219, v dot w, but you can also do like matrix vector product when it fits, right? I mean, this is basically basic linear algebra, but you can only multiply a matrix by a vector when the ranks, let's say, fit, right? The inner ranks fit. So if they fit, then you can do this x dot v, which is the same as multiplying x by v, even though x is a matrix and v is a vector. And by vector, I just mean it's a rank 1 array. It's an array with just one axis. That is what a vector is. And then there's like millions of things you can do. I will leave this more or less here so you guys can take a look later and learn it. But as you can see here, for example, I can call, this is a node version. I can call, for example, np, which is np function from the module, np.sum x. So basically I'm saying I want the sum of all the elements from x. So then I get 10, which is 1 plus 2 plus 3 plus 4. I can also ask for the sum over a specific axis, like for example, over axis 0. And then I get 4 and 6 because this is 1. Oh, let me format this. 4 is 1 plus 3. 6 is 2 plus 4. So then you get 4, 6 because I'm asking for the sum along the axis 0. And then I can ask for along the axis 1. And that gives me 3 and 7 because it's 1 plus 2. 3, and 3 plus 4 is 7. Okay, and then you get all kinds of operations here that you can do. Like for example, this one, log the log of x, and then you get here the log of every element of x, mean and standard deviations of all elements of x, a power of x to the power of 5, which is basically like an element-wise power. And then you get this, the minimum and maximum of x across all dimensions, and so on and so forth. There are literally dozens of these little functions in the NumPy module that you can apply to an array and get something that you need. So always, if you need to do something, first thing you do is go to the documentation and look at it and try to see if if it's already there. If it's something that's like a common thing that many people do, like a mean standard deviation or things like that, usually it's already there. So you just, it's really like a huge toolbox full of stuff for you to use, okay? With this, I will stop NumPy. I think it's enough of NumPy. And then you can, it's enough of NumPy for now. We're gonna jump over to something else now. So just remember this: NumPy arrays, vectorized operations. Okay, when you do something like x times y, you're doing a vectorized operation that is very, very fast. So you should not do this by looping in Python. So whenever you're looping, you must think, could I do the same thing I'm doing without the loop? And if the answer is yes, then do it without the loop because it's much faster.